Hi viewers, today we start F.Sc first physics for the first year students. So physics is actually the study of two things, that is matter, energy, and the mutual relationship between these two. The mutual relationship was given by Einstein from his equation we know that E equals to mc squared. So this equation gives us the mutual relationship of matter and energy. Now let us come towards definition, the study of matter, energy, and the mutual relationship is known as physics, or we can also say the study of the physical world and specific and physical universe in general. Now scope and importance of physics is clear from the following description points. First, we are dependent on physics, so we should study the subject of physical science. That is physics, example, working to driving a car, cooking, to using a gadget, cutting a tree, to building a new house. Even with data intense physics is at work. Physics study the measures of electron in records. It studies the energy in sound waves and electrical circuits. The atomic structure and structure of the universe is also under study of the physics. Drive of the economic engine is also the concentration of the physics, so it needs technologies. Physics generate knowledge and technology develops. Physics of the 20th century discovered so many things like laser, television, radio, computer, internet, DNA, nuclear reactors. Contribution of 10% physics contributes and provide the 10% and technologies are discovered. Other places of importance are improvement, health, telecommunication, transport, and design of our future. System international definition, a complete set of units for all physical quantities, that is for system of units. SI is abbreviated from system international, but written in this form, and international is written with in this form. Version of the name is French. Required quantities. Science requires those quantities which must be defined in many types of quantities. There are two types of quantities. Quantities are of two types of physical quantities and non-physical quantities. Physical quantities are length, mass, time, speed, and force, etc. While non-physical quantities are law, age, kindness, anger, etc. And the earlier times and tests around the world were using different systems of units, that is MKS system, CH system. In 1990, International Committee agreed on a single system for the whole world. Its official name is System International. Here we conclude that we can use other systems and unit works the same, but in science or in physics we must use always the System International. This system keeps quantities and units in two categories: base physical quantities and base units. Second, derived quantities and derived units. The other question, physical quantities and their units. Physical quantities are of two types. First one is the base, the second one is the derived. Similarly, the units, physical quantities units are of two types: base units and derived units. Definition of base quantities: 7,000 or better physical quantities are called base physical quantities. Definition for the base units is the 7,000 or better quantities units are called base units. These are the base physical quantities, and these are the samples, while these are the base units and these are the base unit samples. Now let us go forward. Derived physical quantities, when base physical quantities are multiplied or divided quantities, and these are called derived physical quantities, derived units. The units of the derived physical quantities are called derived units. Now these are the examples for the derived physical quantities: force, area, volume, speed, displacement, structure, up to infinite. You can give examples of the derived physical quantities. These are the samples, and these are the units for the derived physical quantities as I have given is the force, area, volume, speed, etc. So here are the units for the derived physical quantity and derived units, and these are the unit samples. Now, number of derived physical quantities are infinite, while number of base physical quantities only 7 in number. Supplementary physical quantities. These quantities until 1960 will not later in 1995 the general conference of weights and measures group these supplementary physical quantities and to derived physical quantities. Therefore, supplementary physical quantities are two: plane angle, and the second one is solid angle. Its unit is degree, second, revolutions, and also radian, but the radian is the SI unit. Here, solid angle, its unit is still radian. Plane angle, its unit is radian. That is the system international unit for the plane angle. Definition of the radian will be when arc length equals the radius of the circle. Then center angle or the plane angle is known as radian. In simple we write it is RAD equation. Now, number of radians, theta equals to arc length divided by radius. Symbolically, r length is written as h, while radius symbol is small r, and the number of radians is an angle. So therefore, theta equals to h by r is the equation. Value of 1 radian in degree can be calculated. The number of radians in 1 cycle or revolution equals 360 degrees. The number of radians in 1 revolution or cycle equals 2 pi. 2 pi. 2 pi. So now equation 1 and 2, 2 pi radian equals 360 degrees. Now separate 1 radian from 2 pi and then divide both sides by 2 pi. We get finally 1 radian equal to 57.3 degrees. For full revolution or for full rotation, radians will be 2 pi equals to 2 pi radian will be equals to 2 and value of pi equals to 3.1. If you multiply, we get number of radians in full rotation equals to 6.28 radians. The number of radians in 1 degree can also be calculated because we know that 57.3 degrees equals to 1 radian. And now 1 degree is separated from this 57.3. Now divide both sides by 57.3. We get 1 degree equals to 0.017 radian. It means that degree is a smaller quantity while radian is a bigger quantity. Conclusion is radian is bigger than degree. Solid angle when sphere surface area is divided by the sector area, that is r square. This is called solid angle. Mathematically, solid angle is written as a sphere surface area divided by sector area. This is equation 1. Now we know that sphere surface area by r square, sector area equals square of the radius. Now putting these two values in equation 1, so we get solid angle equal to 4 pi r square divided by r square. After cutting of r square with r square, we get solid angle equals to 4 pi radian. 1 radian can also be calculated. If sector area becomes equal to sphere surface area, there is sector area 4 pi r square, and again we put the values here in this equation number 1, 4 pi r square divided by 4 pi r square. Scientific notation: two small numbers written in decimal and power of 10 firm. This is known as scientific notation. Examples of mass of electron is written as 0.0000. So many zeros up to 30 zeros and then 911 kilogram. So in scientific notation, it is easy to write is mass of electron equals to 9.11 10 power minus 31 kilogram. Charge on electron is 0.000 and 18 zeros and then 1602 coulomb. So easy way to write 1.602 10 power minus 19 coulomb. Similarly, Earth mass is bigger mass 6 and then we write 24 zeros and then kilogram is the unit of the mass. So easy way to write mass of Earth 6.0 10 power 24 kilograms. Similarly, mass of Moon can also be write in easy way of scientific notation. There is 1.3 10 power 22 kilogram. Now, prefixes are actually proper names given to certain numbers in power of 10. Examples of 10 power 3, its name is kilo. So, kilo is the prefix of 10 power 3. 10 power 6 is mega, therefore mega is the prefix for 10 power 6. 10 power 9, its prefix is giga. Therefore, wherever we see 10 power 9, we can write giga. Its prefix. Similarly, for milli, micro, nano, these milli, micro, nano also. Now, come to the non-SI units. There are 3 non-SI unit system. It's a non-system international units which are light year, angstrom, and micron. First one is the light year, which is the distance traveled by the sunlight in 1 year in space, moving with the speed 3 10 power 8 meter per second. Therefore, we can calculate the distance traveled, which equals to 9.4607 10 power 15 meter. Example, Milky Way galaxy diameter is 2 10 power 5 light years. Similarly, the spiral galaxy diameter 2 10 power 5 light years. Spiral galaxy near our Milky Way galaxy is Andromeda, which is 2.5 million away, or we can say 2.5 million light years away from the from our Milky Way galaxy. The second one, non-SI unit, is the digit of angstrom, denoted by a degree. Now the non-SI unit of length 10 power minus 10 meter is known as 1 angstrom. 1 angstrom equals to 10 power minus 10 meter. We can also write it as 0.1 10 power minus 9 meter. This equals to 0.1 nanometer. Similarly, examples are that of helium. Atomic size equals 10 power minus 10 meter, which is 1 angstrom. Helium nuclear size is 10 power minus 15 meter. So this becomes equal to 0.00001 angstrom. Helium nuclear size or diameter is 10 power minus 15 meter. This can also be written as 1 femtometer. that is inwards, 1 femtometer in SAM and 1 FM. Now micron, the length 10 power minus 6 meter is said to be micron. Examples are red blood cell or basis diameter or size is 10 microns, or we can also write it as 10 micrometer. Human hair size or diameter is 10 micrometer to 100 micrometer. This equals to 10 microns or 100 microns. Writing unit samples and names printed in Roman upright. Examples are M for meter, S for second, PA for Pascal. Multiple and sub-multiple prefix is a part of the unit. Therefore, we write we write nanometer as nanometer. Together, we write the name with the prefix. Similarly, picometer, so it's the unit. Together we write with the prefix picometer. There will be no space in between unit and the prefix. Multiplication in this space is left between two units, or we can write put a half high center dot in and between the two units. Example is the Newton meter, which is the unit of work or energy. So that is put it over here, or one space is left between the two units. Here is the unit for the work, Newton meter, but one space is left between the two. Joule second, dot is put it here, and here is a space left. And in words, we will write it as joule second. Division oblique or negative exponent is put it, and that is, for example, meter per second or meter per second. Similarly, another example is negative meter per second square, which is the unit of acceleration, can be write as this one or this one. Errors. Now errors are also important, because whenever we measure something, so the measured value do not exactly come equals to the actual value. So let us see types of errors. So basically there are two types of errors: systematic error and random errors. Then systematic errors are grouped into two: instrumental error and personal error. The instrumental errors are then grouped into another two types: positive zero error and negative zero errors. These two zero errors come because of imperfect design and calibration of the instrument. Now let us see the personal error. Personal error occur due to individual carelessness or eye deficiency. How to remove or minimize the two errors, instrumental error and personal error? We improve the experimental techniques, select better instrument, remove personal carelessness. Now let us come to the main second type, that is the random. And this error occur irregularly, random with sign and random with respect to size. These errors arise due to random and unpredictable change in the environmental condition. The environmental conditions which are unpredictable and random, these are change in temperature, change in humidity, wind velocity. Examples: when the same person repeats the same observation in same experiment in varying conditions, he must get different readings every time. There we was. It is enough for today. And next video you will learn more details about errors and the remaining topic of this chapter. So thank you, but please don't forget to subscribe and share. Thank you.